In this video, we're going to go through a review guide covering the major themes and problems that you encounter in Calculus 1. So let's begin. The first one is giving us a function, g of x equals x squared minus 1, and it's asking us to calculate the derivative of this function using the limit definition. So recall, given a function like this g of x equals x squared minus 1, this function will look something like, oh, it's a parabola, it's been moved down 1. It looks something like this. And the way we figure out what the derivative is, we want to calculate g prime of x, is the derivative represents the slope of the tangent line. So given some value x, you imagine, okay, here's some tangent line. And how do we find the slope of this tangent line? Well, we can approximate it using a secant line. And so what we do is we pick a value very close to x, just a little bit bigger, x plus a tiny h. You can go up and you can draw a secant line, a line that passes through both f of x and f of x plus h. So this right here is the coordinate x, f of x, and this right here is the coordinate x plus h, f of x plus h. And the secant line isn't exactly the tangent line, but as this h gets smaller and smaller as h goes to 0, these 2 points will come closer and closer, and the secant line will get closer and closer to the tangent line. So the slope of the tangent line is really close to the slope of the secant line, change in y values, f of x plus h minus f of x, change in x values, x plus h minus x, and then you're going to take the limit as your h goes to 0. So that's just the formula. Well, I've been doing f's here, but I guess I should do this with g's, huh? This is g. This is g of x. We're doing this some function g. Okay. So this just becomes the familiar formula that your derivative is the limit of g of x plus h minus g of x all over, if you have x plus h minus x, the x's cancel, leaving you with just h. So this is the formula that we're going to need to use. So let's do it. Our g of x is x squared minus 1, so we need to plug that into the formula. And you know, that's just justifying the formula. On an exam, of course, you can just use this formula. Hopefully this story reminds you of why this formula is true, but let's just use it. It's going to be the limit as h goes to 0 of plug in x plus h. So you're plugging it in here, so it becomes x plus h squared minus 1. And then you're going to plug in the x. So plugging in x is just x squared minus 1. X squared minus 1 all over h. Okay? Let's try and simplify this sum. You can't just plug in the 0 now, or you'd be dividing by 0. So we're going to simplify it some. Let's see what we get. Take the limit as h goes to 0. Well, here you have on top x plus h squared. So that's x squared plus, not just plus h squared, plus 2xh plus h squared. Right? You have to FOIL it out. So you get this 2xh minus 1 minus x squared minus minus, so plus 1 all over h. There's a few things we can do to make our lives a little bit simpler. The minus 1 and the plus 1 cancel. The x squared and minus x squared cancel, leaving you with just 2xh plus h squared. Notice both of these pieces have an h in it. So we could factor out that h. This is the limit as h goes to 0. Pull out the h, so I'm left with just a 2x, because 2x times h is 2xh, and an h, because h times h is h squared, divided by h. And now we're in business, because now we can divide by those h's, we can cancel those h's, and so we're no longer dividing by 0. So we solve the problem, and now we can just take this limit. As h goes to 0, your 2x is just 2x, but this h right here is going to be going off to 0, because we're assuming h goes to 0. So you're left with just 2x. To recap, our original function was g of x equals x squared minus 1. We found the derivative by using the limit definition, g of x plus h minus g of x divided by h, taking the limit as h goes to 0. We plugged in, and we saw it came out to be 2x. Okay, great. So this reminds us there's this connection between derivatives and limits. The next problem asks us to calculate some limits explicitly. So let's go ahead and do that. The first one is the limit as x goes to 3 of x squared minus 9 over x minus 3. Now you might want to just plug in the 3, but if you do, notice you get on top 3 squared 9, 9 minus 9 is 0, over on bottom 3 minus 3 is 0. This is undefined. This is an indeterminate form. Indeterminate form. So what we need to do is we're going to need to do some kind of algebra, right? And so one trick that you might try is, can we factor anything? Sure enough, the top factors, x squared minus 9 is the same as x minus 3 times x plus 3 all over the bottom, which is x minus 3, taking the limit as x goes to 3. The x minus 3's cancel, so this is cancel. Now we're getting rid of the zeros, because there's the 3 minus 3 that was causing the 0. Getting rid of the zeros, getting rid of the problem, leaving us with just the limit as x goes to 3 of x plus 3, and that comes out to be just 6, because 3 plus 3 is 6. Great. So this first limit comes out to be 6. This problem up here, we had g prime of x was 2x. Here we're finding that this limit comes out to be 6. There's another way, though, that we can solve this. When you run into the problem of this indeterminate form of 0 of 0, we could use algebra. So this was using algebra. Algebra. But we can instead do it with calculus. So another way to solve this problem is you say, well, your limit as x goes to 3 of x squared minus 9 over x minus 3, because it's an indeterminate form, 0 over 0, we can use L'Hopital's rule. L'Hopital's rule. And recall, L'Hopital's rule says that we can take the derivative of the top, the derivative of the bottom, and this limit will be the same. We can only use L'Hopital's rule because it's in this indeterminate form. Otherwise, you can't use it. But because it is, we can activate L'Hopital's rule, and then you take the derivative of the top, the derivative of the bottom, and notice this just comes out to be 2 times x, 2 times 3, which is 6. So we get the same answer either way, by doing this algebra factoring trick or by using L'Hopital's rule. Some of these next problems, though, will really call for L'Hopital's rule. So let's see that in action. Now, there's another limit here that's asking you to find the limit as x goes to infinity of 3x squared plus x minus 9 over 2x squared minus 3. And you might remember the shorthand rule. Like, there's this trick that just says if you have a polynomial over a polynomial and it's going off to infinity, then it's like, you know, when you're dealing with like infinity and like, you know, like a billion squared, you know, really, really big numbers, a trillion, these smaller terms like the plus, the 3 and the -3, the -9, it won't really matter. All that matters are these big terms. So you can ignore the smaller ones, and you're like, oh, that just comes out to be 3/2. It's just 3/2. But if you want some justification for how we get there, we're actually using L'Hopital's rule. Because if you try to plug in infinity, on top you would be getting infinity, on bottom you'd be getting infinity. So that's an indeterminate form. That's one of the two forms that calls for L'Hopital's rule, infinity over infinity and 0/0. And so you could L'Hopital this guy, and you could say, hey, by L'Hopital's rule, this is the same thing as the limit of the derivative of the top, which is 3 times 2x plus 1, over the derivative of the bottom, 2 times 2x. Notice these smaller terms disappeared when we took the derivative. These smaller pieces died. And then, if you try and plug in infinity, you'd still have infinity over infinity. So it's still indeterminate. So we need to use L'Hopital's rule again. But then notice what happens. Now these x's are going to die. So this 1 disappears, you're left with just 3 times 2. And on bottom it's just 2 times 2. And those pieces cancel, leaving you with just the original ratio. And so every time that's going to happen, if they're the same power, then you just look at the leading power and you just look at the ratio, and that'll tell you what the limit is. So this guy comes out to be 3/2. This last one's a little bit wacky. It's asking you to find the limit as x goes to infinity of an integral 1 to x of 1/t² dt. And so I'm just going to forget that the limit sign is there and just focus on this integral to begin with. And so I'm like, okay, I need to first find the antiderivative of this guy. This is 1/t², same thing as t to the -2. So it's going to bump up to t to the -1, and then I drop in front of it 1/-1, or just a minus sign, the reciprocal of -1. And I'm going to plug in 1 and x. So plugging in x, I get minus x to the -1, which is -1/x, minus plug in 1, -1/1. So this just comes out to be -1/x minus plus 1. But I still need to take the limit. So I'm taking the limit of this as x goes to infinity. I'm taking the limit of this as x goes to infinity. I'm taking the limit of this as x goes to infinity. It comes out to be as x goes to infinity, well, this piece just goes to 0. 1 divided by a huge number vanishes. So you get 1. Which maybe doesn't seem that impressive, but like, stop and think for a second what this is saying. Like, what does this guy mean? This is saying the area under the curve. So it says if you were to graph out the graph of 1/t², so that looks something like this, getting closer and closer and closer and closer to your x-axis. This is y equals 1/t², and you were beginning at 1, and you calculate the area up to some x value, but then you let that x value get bigger and bigger, go to infinity. So you take all this area, we just found out that that total area comes out to equal 1. So that's the graphical meaning, or the geometrical meaning behind this poem. This limit is 1. Okay, this next guy has us consider a function, and maybe we'll just do it here on this paper. Well, I guess I can do it on this other paper so you can see it nice and big. Our function is f of x equals minus x cubed plus 3x² minus 2. And we're going to try and sketch a graph of this. And so we want to sketch a graph of it here. And to do that, they have us walk through and think about all these different things, like what are the limits, where are the maximums and minimums. And so let's go ahead and work through that. And so let me just clear some space. We're thinking about first of all, what's the limit? So like, what's the limit of this guy as x goes to minus infinity? And what's the limit of this guy as x goes to positive infinity? And what you should think is, again, it's the largest term that dominates. The smaller powers don't matter. And so you just need to think, okay, this looks like negative x cubed. What does that look like? Well, you know x cubed looks something like this. So negative x cubed will look the opposite, something like this. So as I go off to the left to negative infinity, as x goes to negative infinity, I'm going up to positive infinity. And as I go to the right towards positive infinity, my graph's going down to negative infinity. Another way to think about it is if I plug in a really big negative number and I cube it, it's still really negative. But then I take the negative of that, making it positive. That's why this is positive infinity. Whereas if I plug in a really big positive number and I cube it, really big positive still, but then I take it negative, I'm making it a really big negative number. Okay, so that's the end behavior, where it goes to the left and to the right. Now we want to think about maximums and minimums. So remember, to think about maximums and minimums, the first thing we have to do is find our critical values. We want to think about where's the derivative of this guy 0. So we find the derivative. It's negative 3, the power drops down, decreases by 1, plus 2 drops down, making that into a 6, decreases by 1. The 2 vanishes, so this is just my derivative, which is the same thing as, well, let's see, I can pull an x out. Oh, I could pull the 3 out as well, leaving me with negative x plus 2. And I want to know, to find my critical values, where is that 0? Well, either 3x is 0, in which case x is 0, or negative x plus 2 is 0, which means my x must be 2. So these are the critical values I should check. And so what I'll do is I'll make a little line. These are my x values, and I'm thinking about what's going on with the derivative. I have 0 and 2, and at those values, we just said the derivative is 0. And now what we're going to do is test some points in between and try and think about what the derivative does. So intermediate value theorem tells us that if I'm negative at one point, I'll be negative at the whole interval. If I'm positive at one point, I'm positive in the whole interval. So we just need to check one point on each interval. So for instance, over here, you might test like negative 1. If you plug that into your derivative, not the original function, the derivative, you get a negative times a positive, comes out to be a negative number. So negative derivative means my function is decreasing there. If I go and plug in a number between 0 and 2, like I plug in a 1, I get positive times a positive, so that's positive. So my function's increasing there. And if I plug in a number bigger than 2, like 3, I get positive and negative, so it's negative. So my function's decreasing. Well, there's a lot of things I can say now. First of all, notice I was decreasing, then increasing. So at this critical value, he must be well, it's like going down, then going up. He's like at the bottom of this hill. He's a minimum. Here, I was increasing, and then I get to the value x equals 2, and then I start decreasing. So at x equals 2, I must have a maximum. So let me summarize all this. I have a local min at x equals 0. I have a local max at x equals 2. It's not the global min or global max, because you know this function is going to be shooting down and shooting up towards infinity and negative infinity. And so these aren't the global ones, but the local mins and local maxes. And then I know it's decreasing from all the way up to 0, so from negative infinity up to 0, and union from 2, x equals 2, all the way to infinity. And I know it's increasing from 0 to 2. That's where the derivative was positive. 0 to 2. Okay. The last thing we want to ask about are your concavity questions. When is it concave up? When is it concave down? Do you have an inflection point? And so to help us think about that, we need to take the second derivative. So here my function, original function, we took the first derivative. That let us think about when it was increasing or decreasing, find our max and mins. Now we want to take the second derivative. We get minus 6x plus 6. Okay? Let's see where it's 0, and then that'll help us figure out where it's positive, where it's negative. So we set this equal to 0. Just like in the previous one, the first derivative, we're doing the same process with the second derivative. We want to solve where this guy's 0, just like we did before. Well, if negative 6x plus 6 is 0, you can move the 6x over, divide by 6, you get x equals 1. And so, very similar to before, just like how we made this line last time, we're going to make a line to look at x values and ask what's the second derivative doing at those values. So 1, we know it's 0. If you test something smaller than 1, like 0, you get 0 plus 6, that's a positive number. Positive second derivative means that you're concave up. If, however, you test a value bigger than 1, like 2, then you get like negative 12 plus 6, still negative. It's a negative number, so it's concave down. And so we can conclude that our graph is, just like before how we did this analysis, we say we're concave up from negative infinity all the way to 1, everything up until 1. And we're concave down from 1 all the way up to infinity. And we can also notice that since we changed concavity from concave up to concave down, here where we have this derivative, second derivative of 0, this is an inflection point. At x equals 1. So we've now done quite a bit of analysis on this function, from looking at its end behavior to its first derivative to its second derivative. And so let's use all that to now go back and graph this function. So I know it's going to, what I like to do often is just draw little lines on this graph that help me. So from, let's see if we can put this all on screen. Maybe I can just, from my first derivative, we found out I have a local min at x equals 0. So here at x equals 0, I have a local min, and I have a local max at x equals 2. What I'm going to do is actually plug in those numbers into my function to find out what they are. Now, when I plug in 0, f of 0, where am I at? Where's my function at? Well, my function is x cubed plus 3x squared minus 2, so plugging in 0 is going to negative 2. So at 0, I'm at negative 2, and we know that's a local min. We said that's a local min. Similarly, I can plug in 2 into my function to see what it comes out to be. I plug 2 into my function, and I get negative 8 plus 12, which is 4, minus 2, which is 2. So here I have a local max at 2. And we said that our function is decreasing before this guy, then it's increasing, and then it's decreasing. So I'll just put some lines like that to indicate. So we know it's going to look something like decreasing, increasing, and then decreasing. But we might want to then think about how's the concavity inform what's going on here. Well, it's concave up till the point 1. So we have this other special point at 1. When x equals 1. When x is 1, what is our function? Well, f of 1, if you plug into the original function, you end up with 0. So it's actually right here, it's an inflection point. And we know before 1, we're concave up. So before 1, we're concave up, and after 1, we're concave down. So all of this should be bending up, and all of this should be bending down. So now I've combined the information from increasing and decreasing with the concavity information to make a nice little sketch of this function. Okay, good. The next problem is a little more interesting. It doesn't seem to be a straightforward calculation, but rather it's showing us 3 different graphs. I'm going to color them so they pop out nicely. The first one is called graph 1, and it's this little, looks like a bell curve, if you're familiar with that, like a little normal distribution. The second one is number 2, and it's got a hump going up, and then it falls down, and then it comes up like this. And then we have number 3, so let me maybe use like blue, or this is purple. Number 3 is going to come up and fall down. And over here I'm asked, okay, if which match 1, 2, and 3 with these functions where this is f of x is the first one, the second one is f prime of x, and the third one is the antiderivative of f of x. And so what I should think is, I'm like, oh, wait a second, these are not like 3 arbitrary things. These guys are related to each other. Like, how are they related? Well, by taking the derivative, it moves me from f to f prime. So taking d dx, taking the derivative, I move from f to f prime. Now, this guy is the antiderivative of f, which means if I take the derivative of the antiderivative, I'll also be moving back from the antiderivative of f to f. And so I'm trying to figure out, like, so each of these is derivative of another one. So over here, I want to figure out a similar relationship. I have these different functions. I'm trying to figure out which one is the derivative of which one. And so I'm going to look at it. I'm like let's go to function 1. It's like, does he have a derivative? Well, I know right here, like, notice, like, let me get a, as I move along function 1, as I move along this first function, I have a maximum right here, so I know its derivative is going to be 0. So right there, the derivative is going to be 0. And before that, the derivative is increasing, and after that, the derivative is decreasing, which looks exactly like what function 3 is doing. It's 0, it was increasing before, it was positive before, and it was negative after. So this yellow function is increasing, maximum decreasing, which means its derivative is positive, 0, negative. And so I'm going to guess that from function 1, it probably has as its derivative function 3. Okay, so now what happens with function 3? What does its derivative look like? Well, right here you have a maximum, so you expect its derivative to be 0 right there. And right here it has a minimum, so you expect its derivative to be 0. Before this maximum, it was increasing, so its derivative should be positive. After this maximum, it's decreasing, so its derivative should be negative. After this minimum, it's increasing, so its derivative is positive. And so function 2 appears to be the derivative of function 3. And so now we have to line these up. So if the first one is function 1, and then his derivative is 3, and then his derivative is 2. Over here I have this bottom one, the antiderivative. His derivative is f, and then his derivative is f prime. So this bottom one must be 1. Its derivative is 3, so his derivative is 3. 1, 2, 3. And his derivative is 2. 1, 2. Cool. Victory. And now I'm just realizing this might have bled through. Yeah. This bled through really bad. Let me see if I have another copy. I do not. So I'm going to go grab another copy. I'll be right back. Okay, I got a fresh copy, so let's get going. Next problem. We're given a function, but this one is going to be defined implicitly. That is, your x's and y's are mixed together. You have y squared plus xy plus x squared is 3. And we're going to try and solve for y prime. And so how do you solve for y prime? Well, you just take the derivative of the thing. You don't care that it's mixed together. You just take the derivative. But you imagine that your y is a function of x. So you're thinking in your head, you're like, okay, we're going to treat y as some function of x. So when I see things like y squared, you're like, what does that mean? Well, if it had been some function of x squared, you know how to find the derivative. The derivative of that comes out to be, what? 2 times the function times the derivative of that function, right? And we're still going to do the exact same thing. You say the derivative of y squared is just 2 times y, but then times the derivative of y, which I'll call y prime. So that's the basic rule we're going to remember. It's treating y as some function of x. So right here, we're going to take our derivative. So we're going to move by taking the derivative of everything, d dx. Y prime becomes 2y, y prime, plus xy. Oh, product rule is a product. So I have to hold the first, take the derivative of the second, the derivative of y as its derivative, y prime, plus hold the second, y, take the derivative of the first. The derivative of x is just 1. And so that's just 1. So we're going to left just a y there. Plus, the derivative of x squared is just 2x. And you're like, don't I have to do times x prime? Well, that's just the derivative of x, which is times 1, so you don't have to worry about it. It's only with the y's that you have to do y prime. Then it comes out to equal the derivative of 3, which is 0. So now what we're going to try and do is get all the y stuff on the same side. Like here I have 2y, y prime. Here I have x, y prime. But these other things I'll move to the other side. So I'll move this y over as minus y. And I'll move this 2x over as minus 2x. And since I only have only y prime stuff on this side, I can factor it out. It's like, look, I got this y prime piece, this y prime piece. So let's just factor out the y prime, leaving you with 2y plus x equals minus y minus 2x. And then I can solve and say y prime must be minus y minus 2x divided by 2y plus x. And so now I've solved for y prime. The problem then goes on to ask for a second thing. It says, what's the equation of the tangent line at the point 1, 1? So notice 1, 1's a solution to this. If you plugged in 1, you'd have 1 squared plus 1 times 1 plus 1 squared. And this comes out to be 1 plus 1 plus 1 is 3. So 1, 1 lies on this graph. And so we want to know, so this is some curve. I don't know what it looks like. It's some curve, but it has the point 1, 1 on it. And we're trying to figure out what's the tangent line there at 1, 1. So let's come down and think about that. Trying to find the equation of my tangent line at 1, 1. Well, I already have one piece of information about this tangent line. I already know it has to pass through the point 1, 1. So what else do we know about this tangent line? Well, we also know that the slope of the tangent line is going to be the y prime value. Like, what is the slope? Well, the slope is just whatever y prime is at 1, 1. Y prime at 1, 1 is just plug in your 1 and your 1. You get negative 1 minus 2 times 1, minus 2, over 2 plus 1, which is negative 3 divided by 3. Negative 3 divided by 3. It's negative 1. So you have this point, 1, 1, and slope negative 1. So let's put those pieces of information together. You know, you're like, well, you use point slope form if you know it. It's just y minus your y value equals your slope times x minus your x value, 1. And then you can simplify this. This just gives you that this is negative x plus 1. You bring this 1 over as plus 1. So you get y equals negative x plus 2. Or we could have done y equals mx plus b, say y equals negative x plus some b, and then use this point to figure out what b has to be. Either way, you get the slope of the equation of your tangent line is y equals negative x plus 2. Okay, next problem. Next, we're looking at an optimization problem. It says consider the graph y equals the square root of x. So that looks something like this. Oh, it shouldn't be. It's not defined over here. Something like this. And we want to know what point is closest. What point on this graph is closest to the point 3, 1, 2, 3, 0. Who's closest? And you're like, I don't know. Is it this guy? Is it this guy? It's not clear. Well, whatever the point is, it's going to be some point on here. It's going to be some point of the form x, y. And we're trying to figure out how you can make it as close as possible to this other point, 3, 0. So we want to minimize the distance, which is the square root of the difference in the x values, x minus 3 squared, plus the difference between these y values, y minus 0, just y squared. Well, the problem is it's a function of two equations. It's like I have x's and I have y's. Oh, but I know what my y is. My y is the square root of x. And so I can simplify this and say I actually want to minimize the square root of x minus 3 squared plus the square root of x squared, which is just the square root of x minus 3 squared plus x. And now it's just a function of one variable. That's going to let me calculate the derivative and find out where the derivative is 0. Because the minimum happens when the derivative is 0. But I look at this and I'm like, I don't want to deal with that square root. Fortunately, I don't have to. Just remember, the square root of this whole thing is at a minimum when the inside is at a minimum. So instead of minimizing this thing, I can just minimize instead the inside, because if you make the inside as small as possible, then the square root of it will be as small as possible. So I'll call that like something like big D, and I'll just make it the inside part. So we just really need to minimize this part. So let's minimize it. Let's take the derivative and set it equal to 0. So we call minimum occurs when the derivative of d is 0. So we can go ahead and take this derivative, 2 times x minus 3 times the derivative of the inside, which is 1, so you don't really have to worry about that, plus the derivative of x, which is 1, set that equal to 0. So this is 6x minus 6 plus 1 is 0. So this is 6x minus 5 is 0. So x equals 5 over 6. Now, you might be concerned, like, how do I know this is a minimum and not a maximum? And maybe it's obvious from the problem that, like, it's not going to be like a local maximum. It's It's a local minimum. But if you really want to fuss about it, what you could do is you could do this analysis we've done 1,000 times now, where you look at the value x equals 5 over 6, and you say my derivative there is 0. And what happens a little bit smaller if I plug in something smaller than 5 over 6? And so you can look at your function, like something like a half. You can think about what happens if I plug in a half. And, well, it's like 2.5 squared, negative 2.5 squared, which, it's some number, but it's definitely positive. It's definitely a positive. Oh. I'm sorry, I should be plugging this into my derivative. If I plug in like a half into this derivative, if I plug a half into here, I'll get like a 3 minus 5, which is negative 2. So I get a negative. Plug into the derivative, it's a negative, so it's decreasing. And if I plug in something bigger, if I plug in like 1, you plug 1 into this, notice now it's positive. 6 times 1 is 6, 6 minus 5 is 1, so it'll be positive. So it's increasing. So sure enough, at 5/6 we have a minimum. So that's where a minimum happens. We have a minimum when x is at 5 over 6. Or you would say your minimum is at the point 5 over 6, and then the y value is just the square root of 5 over 6. And so that's the point on here that's closest to 3, 0. It's 5 over 6 and the square root of 5 over 6. Okay. Let's go on to the next one on this review guide. It's asking us to, it says we want to make some kind of can, a cylinder can, that holds 100 cubic centimeters of water. So let me draw a little picture. I'll make my can like black. So it's a cylinder. And I want to make sure that the volume comes out to be 100 cubic centimeters. And I want to know what are the optimal dimensions. And so I should give some names to these dimensions. I call one of them is like height. And we can call some radius little r. And I want to, what are the optimal dimensions to minimize, what I want to minimize, the amount of material used, so like the aluminum that's being used to create this can. And so that's going to be, well, what is it's not the volume, that's fixed, the volume's 100. It's going to be the surface area. I want to minimize the surface area. So let's see if I can get equations for these two, my constraint, my volume, which is my constraint, and my problem I want to optimize, which is my surface area. So let's try to get expressions for them. So I'm told that my volume is base times height. So my volume is pi r squared times height. That's my volume. And that's fixed. That has to be 100. But then I want to minimize my surface area. So how do we think about this? Where we said the can has a top and a bottom. Those each have area of pi r squared. So you have pi r squared on bottom, pi r squared on top, so 2 pi r squared. But then there's the side of your can, which if you were to unfold this, the side of it, if you were to unfold this part of the can, if you were to cut it off and unfold it, it would be a rectangle. A rectangle that's h high, but then the length of the rectangle would be the circumference of your circle, because it wraps around the circle, which is 2 pi r. And so the area of this third piece is 2 pi r times h. And I'll just call that S. This is what I want to minimize. Well, minimums happen when the derivative is 0, so we want to take the derivative and set it equal to 0. But problem, we have two variables going on. We have both r stuff and h stuff here. So before we take the derivative, we need to get rid of one of the variables. Like, can we get rid of this h somehow? Well, yeah, we can use this equation to help us get rid of h. Use our constraint to say h we know has to be the same thing as 100 over pi r squared. So that lets us get a new expression for surface area. My surface area is actually 2 pi r squared plus 2 pi r times 100 over pi r squared. And immediately there's some simplification that takes place. A pi and pi cancels, a radius cancels with one of the two radiuses on bottom. So we're left with your surface area is 2 pi r squared plus 2 times 100, 200 over radius squared. Now we can take the derivative of this and find when it's 0. So I'm going to be taking the derivative with respect to radius. And I want to know when is it 0. So it's going to come out to be the radius of the power drops down, so it becomes 4 pi times my radius plus, this is r to the negative 2. So the negative 2 drops down, so it's a minus. So negative 2 drops down, making it minus 400 times r to the minus 3. Okay, if I want to know when that's 0, I can move this to the other side. I get 400 r to the minus 3, which is 400 over r cubed, equals 4 pi r. I'll move my r cubed over, and I'll get that 400 is 4 pi r to the 4th. And so that tells me that r to the 4th is 400 divided by 4 pi, or that's the same thing as 100 divided by pi. And so my r is just the 4th root of 100 over pi. And I don't know what that is off the top of my head, but let's figure it out. I have 100 over pi. Oh, I don't know where the pi symbol is on here. Pi. And then I want to raise that to the 4th root, or to the 0.25 power, so the 1/4 power. 2.375 about. So that's about 2.375. And now you might be like, okay, so what should our height be? Because remember, your height is going to come out to be 100 divided by pi r squared. So now you can plug this in. You're like, okay, well, we just found out that my radius is going to be 2.375 or something along those lines squared. So that's going to be 100 divided by, in parentheses, pi times 2.375 squared and we get 5.64, which is actually twice the radius. So you just get a 5.64, which comes out to be 2 times the radius. And so the optimal dimensions of a can to minimize the amount of material happen when your height is 2 times your radius. And remember, 2 times your radius is just your diameter, right? So the optimal dimensions actually happen when your height and diameter are the same, which isn't what a Coke can is. Like, a Coke can is much taller than it is wide. It's something much flatter and wider. So that's the optimal. There's a nice symmetry going on there. Okay, here's another problem. Not quite optimization, but related. This is a related rates problem. We have air is being pumped into a spherical balloon. So we have some sphere, and air is being pumped into it. So you have air is coming in at a rate of 5 cubic centimeters per minute. We want to know how quickly is the radius expanding. So this is my radius. When the radius is 10 centimeters. So we're going to focus at the time when the radius is 10, but it's changing. You know, this thing is growing as air is being pumped into it. So the two things we're concerned about are radius and volume. Notice so we're concerned about the volume and the radius. The 5 is how much the volume is changing. You're pumping into it another 5 cubic centimeters of volume every minute. So we're being told that the change in our volume is 5. And we're being asked how quickly is the radius changing. So that's telling us that the dr dt is the unknown. And so we want some way to relate these rates. So how can we relate the rates? Well, how do we relate v and r? Well, for a sphere, your volume is 4/3 pi r cubed. So now we related the two things we're interested in, volume and radius. Volume and radius. And so to get to dv dt and dr dt, we now need to take the derivative, taking the derivative with respect to time. The derivative of volume with respect to time is just the derivative of volume with respect to time, dv dt. Times, our 3 is going to drop down when we take the derivative of this. So it becomes 4 pi r squared dr dt. This is just like implicit differentiation. We're saying volume and radius change with time. So you're thinking of your volume as being a function of time. So its derivative is just however it's changing. Radius is some function. And so you do the derivative by dropping the power down, but then by a chain rule, it's times the derivative of that function with respect to time. Or you could call this like v prime and r prime. But now we can plug in everything we know. We know that dv dt is 5. We're told that we're concerned about when the radius is 10. And we want to figure out what is dr dt. And so then you can just solve. And you get that dr dt is 5 divided by 400 pi. Which you could simplify, that's 1 over 80 pi. And that's the rate at which this is centimeters per minute. The same units as before. Centimeters per minute. Okay, it's a very small change. Because the radius is quite large, and so when you add an extra 5 cubic centimeters, the balloon doesn't have to grow by that much. It grows very slowly. Okay, one more related rates problem. In this setup, you are driving, the problem says you're driving east or to the right at 40 miles per hour. So here you are, and you're driving at 40 miles per hour. Just got a ticket the other day for going a little bit faster than that. No, not 40. You're going 30. You're only going 30. Your friend is going 40. So here's your friend down here. And your friend's going 40. And you're both headed to the same point. And we're assuming that you're setting up at some time where at this moment you happen to be 4 miles away, and your friend happens to be 3 miles away. Well, that's changing. You're getting closer, your friend's getting closer. And we want to know how quickly is the distance between you and your friend changing. So we'll call that like big D. How quickly is that changing? So we're interested in what is the change in x? What is the change in this distance, is big D. I should give some names for your distance and your friend's distance. And so x and y are good names. Your distance, your friend's distance. And so what is 30? Well, 30 is just the change in x over time. Except notice x is getting smaller, so it's actually dx dt is minus 30. And what is 40? Well, that's just the change in your y over time. But notice that since y is getting smaller, it's actually minus 40. It's negative 40. So we should have all the information we need. We have these rates, dx dt, dy dt, and we will relate them to your dd dt. So how are x and y related to distance? Well, Pythagoras tells us that your distance squared is x squared plus y squared, right? This is the right triangle, so this is Pythagoras' theorem. And so now we can get the rates by taking the derivative with respect to time. And so treating this as these are all functions of time, I'll change them with time. You get 2d dd dt equals 2x dx dt plus 2y dy dt. And now we can plug in everything we know. So our distance is, oh, what is my distance? Well, I'm at this moment when x is 3 and y is 4. So you would have 3 squared plus 4 squared, that's 9 and 16, that's 25. So your d comes out to be 5. So I get 2 times 5 times dd dt, that's what I don't know, equals 2 times x, my x is 3, 2 times 3, times dx dt, oh, dang it, this is y and this is x. So my x is actually 4, 2 times 4, times dx dt, which is minus 30, plus 2 times y, which is 3, times dy dt, which is minus 40. So we end up with 4 and 3 is 12, so that's 120 times 2, that's minus 240. And here I have another minus 240. Here I have 10 dd dt, so I end up with dd dt is, well, this is 2, this is minus 480, but then I divided by 10, so it's negative 48 miles per hour. And I just think this is beautiful. You're only driving at 30 miles per hour. Your friend's only driving at 40 miles per hour, but the rate at which you're getting close to each other is 48 miles per hour, which kind of makes sense. You know, if you had been going straight towards each other, you would be getting closer at 70 miles per hour. You know, but you're not going straight towards each other, you're going towards a common point, so it's not quite 70, but it's faster than either one of you are traveling. So that's quite nice. Okay, let's see. What do we have next? Next, we're given a series of true and false statements. And so let me maybe get this a little bit closer so you can see them a little bit better. So we have these true or false statements. And let's just talk through them. All continuous functions are polynomials. Well, continuous, remember, means you have no jumps, no gaps, no holes. There's lots of continuous functions. So yes, polynomials are continuous. It is true. If you're a polynomial, then you're continuous. But there's other kinds of continuous functions too, like sine, you know, sine and cosine. These guys just go up and down, and those are also continuous. So you can be a continuous function, like sine of x or cosine of x, and not be a polynomial. So this is actually false. Not all continuous functions of polynomials. False. It is impossible for a function to have both a horizontal asymptote and a vertical asymptote. So it's like, okay, horizontal asymptote, what is that? That's something like, you know, duh. Vertical asymptote, it's something like duh. Can you have both? Of course you can have both. There's all kinds of functions that have both, like y equals 1 over x. It's one we've seen many times. He gets close to both his horizontal and his vertical asymptotes. So that is false. So I should use the same color. This guy is also false. You can have both. The function f of x is the absolute value of x is continuous at x equals 0. So what does this guy look like near x equals 0? Absolute value, remember, looks like this. Because the positive numbers just become themselves, the negatives get flipped up. So absolute value looks like this. Now, we do have a sharp point there. So what does it mean to have a sharp point there? Well, that means it's not differentiable. Because the limit from one side is different than from the other side when looking at the slope of the tangent lines. But the function's continuous. I didn't lift up my pen when drawing. There's no jump or anything. So although the slope changes and there's a jump in slope, the function itself is continuous. So it's not differentiable, but it is continuous. So is it continuous? True, it is continuous. The derivative of a polynomial is a polynomial. Well, for that one, you just have to remember, what is a polynomial? It's just made up of, something like 2 times x to the 5th or whatever. And when you take the derivative of that, 5 just falls down. It becomes like 10x to the 4th. Or, it's still a polynomial. It's just something times x to some power. And you might be like, well, what if it was just something like 3x? Well, what's its derivative? Well, it's just 3. And, 3 it's a constant function, but still considered a polynomial. So we still consider constant functions polynomials. They're really dumb, simple polynomials, but it's still a polynomial. So that's also true. The derivative of arc cosine is arc sine. Now this is throwing you off, minus arc sine. It is true the derivative of cosine is minus sine, but the derivative of arc cosine is this complicated -1 over the square root of 1 minus x squared. So that's false. That's just seeing if you remember the derivatives of sine and arc cosine. The integral of a constant is a constant. It's like, well, just test it. What's the integral of 2? It's like, does it come out to be a constant? No, it comes out to be 2x plus e. It has plus a constant at the end, but it's not a constant. It's 2x. And so that is false. Okay. So that was pretty good. False, false, true, true, false, false. Okay, let's try this next section that has us calculate some derivatives. So I'm just going to go through and rapidly calculate them and see if we can knock this out pretty quick. So first we have the derivative of x cubed minus 2x plus 1. And this is going to come out to be 3x squared minus 2. So there we go. That was simple. Next we have, so just the power falls down. And when it's 2 in front of x just becomes 1. So simple. How about the derivative of x squared minus 2 to the 4th? Well, here we have to do the chain rule. We have the power drop down. We leave the inside the same. So it's like you've locked in the inside part. We'll leave that the same. The inside's going to stay the same. So the 4 is going to fall down. But then you're going to times it by the derivative of the inside. And what's that? Well, derivative of x squared is 2x. The minus 2 vanishes. So you just get this. Okay, let's do another one. The next one's asking us for the derivative of the square root of 3x minus 1. It's like, okay, square roots, that might seem confusing, but just remember the square root is the same thing as the half power. So it's 3x minus 1 to the half power. And we get half power falls down, 3x minus 1 to the minus 1/2. Now I just left the inside the same again. This inside part, I just left it the same, but now I need to times it by the derivative of that inside part, which is just a 3. If I wanted to, I could rewrite this as I have 3 over a half 2, and this negative 1/2 is the same thing as 3x minus 1 square root. I'm bottom because it's negative. Square root because it's a half. You could leave it like this also. You probably write 3 halves, combine the 3 and a half. But you could leave it as the negative 1/2 power, or put the square root on bottom, and that's fine. Oh, this next one, very clever. What's the derivative of the natural log of pi? Now watch out, because you might be like, wait a second, natural log, what's the derivative? But no, it's a trick. Pi is just a number. And when you take the natural log of it, it's still just a number. So this is just a constant. So it's like 17, it's not 17, it's more like 1.9 I don't know what. It's one, you could type it into a calculator if you had one. And you could be like, what is the natural log? I'm not familiar with this calculator. Natural log, so pi, take its natural log. See, it's a number, it's 1.1447, just some constant. And so when I take its derivative of a constant, it always comes out to be 0. Now you might be like, wait a second, I thought it's like for natural log, you do 1 over that number. Okay, no, because if you're going to do it this way, then you should think by the chain rule. It's 1 over the inside times the derivative of the inside, and what's the derivative of pi? Well, it's a constant, so it's 0. So even if you messed up, the chain rule would remind you, yeah, it still just ends up being 0. So just 0 because it's a constant. Don't do this bottom way. Just think it's just a constant, so it's 0. But even if you did do it as 1 over pi, the chain rule should remind you have times it by 0, so it ends up being just 0. Okay, here's a few more. The next one on the sheet is asking you for the derivative of sine of x squared minus sine squared of x. And this is just testing to make sure you really understand the notation of what's going on, right? It's like, here I have sine of a function. So by chain rule, I take the derivative of the outside, it's cosine, and then I leave the inside the same, times the derivative of the inside, 2x. That was my chain rule. Minus, but what's going on here? Well, when you see sine squared, remember that's the same thing as saying the whole thing, sine of x, the whole thing being squared. So now the square root of function's on the outside instead of the inside. So when I take the derivative of this piece, the 2 is going to fall down, leaving the inside the same, sine of x, times the derivative of the inside, the derivative of sine, times cosine. So there that is. Okay. Here's another clever chain rule one. The derivative of sine of cosine of tangent of x. And so our strategy here is we're going to remember that when taking the chain rule, you leave the outside one, take the derivative of the outside one, leave the inside the same. So in our first step, we're going to take the derivative of the outside, derivative of sine is cosine, and we leave the inside the same. So we leave the inside as cosine of tangent of x. So I just left this inside the same. But now I need to times it by times the derivative of the inside. So take the derivative of this part. I say, well, I'm going to take the derivative of the cosine part and leave its inside, the tangent, the same. So derivative of the cosine becomes minus sine, and leave tangent the same, leaving tangent of x the same. And then we said, okay, we left the tangent the same, but to finish off the chain rule, I need to then times it, so it's all been times together, by the derivative of tangent, which is secant of x times tangent of x. So I know this is a mess, but it's cosine of tangent times negative sine of tangent times secant times tangent. Okay, a couple more here. What's the derivative of x ln of x? Well, by the chain rule, this is just going to, not chain rule, it's a product rule, sorry. It's not a function inside a function. Instead, you have a first piece and a second piece being times together. So we need to use the product rule. So we say, keep the first one the same, hold the first, times the derivative of the second. Derivative of natural log of x is 1 over x. Plus, hold the second, ln of x, derive the first, derivative of x is 1. And simplify this, x divided by x is 1, plus ln times 1 is just ln, natural log of x. One more, couple more. Derivative of sine inverse of 3x. So in general, you might want to like just stop really fast and be like, wait a second, this is sine inverse, this is arc sine stuff. Let's just go back and remember these formulas. For arc sine of x, it's 1 over, I hope I have this right, I think it's 1 minus x squared, square rooted. For, that's sine. For tangent, derivative tangent, oh, this is sine inverse, tangent inverse. Derivative tangent is secant tangent has two pieces. Similarly, the derivative arctangent has two pieces. It's the first piece is x and the second piece is the square root of x squared minus 1. I think that's right. And then the derivative of secant inverse of x, I believe, is 1 over 1 plus x squared. Oh, no. The derivative tangent is secant squared. Oh, okay. No, I'm sorry. These are backwards. The derivative tangent inverse is 1 over 1 plus x squared. The derivative secant inverse is 1 over x times the square root of x squared minus 1. Yeah, because the derivative secant is secant times tangent, which is two pieces. The derivative tangent is tangent squared, and that's why there's no square root. Okay, so that's what's going on here. And then remember, if you want to do like cosine, it's just the negative of this, right? Like, what's the derivative of cosine inverse? Arc cosine is also called. And it's just cosine, so it's the opposite. It's negative 1 over what you get for sine inverse, the square root of 1 minus x squared. And similarly, the derivative of cotangent inverse would be negative this. And for cosecant inverse, it would be negative this. So you should know these, know them well. But for sine, it's really easy. You just plug in 3x instead of x. And so we'll find the derivative of arc sine, or sine inverse, of 3x. That's just 1 over 1 minus 3x squared, square rooted, which is 1 over 1 minus 9x squared. Both the 3 and the x get squared. Okay. The last one of these derivatives, we're now up to like the boss, right? Gotta defeat this boss before we can win this game, is x to the cosine of x. And it's like, this is really tricky. It's like, you can't just use the power rule because you have an x in the power, and so, you know, it doesn't work. And you can't treat this as exponential because you have x's in both the base and in the power. It's in both places. And so remember, the trick here is you say, well, consider some function like y equals x cosine of x. The problem is you have x's in both places, in both the base and in the power. And so to make our lives better, we want to somehow move the cosine down. Well, there's only one way we know to do that, and that's by taking the natural log of both sides. So then you get the natural log of y equals the natural log of x to the cosine of x. And now you can use your properties of natural log to move the power down. Cosine of x times ln of x. Over here you still have ln of y. Now that we've made it simpler, I mean, it's more complicated because natural logs involved, but it's simpler because it's no longer an x to an x. It's just a multiplication instead of a power. Then you take the derivative. So now we come through and we say, okay, what is the derivative? ddx. And so we say the derivative of natural log of y is y prime over y. And it's 1 over y times its derivative. So y prime over y. And then here it's a product, so it's a product rule. Hold the first times the derivative of the second. Derivative of natural log is 1 over x. Plus hold the second, drive the first. So you keep ln of x the same, and you times that by the derivative of cosine, which is negative sine of x. And so then you get that your y prime is, it was cosine of x over x minus natural log of x times sine of x. That's what your y prime divided by y is. And so your y prime is just this whole thing times your y. And what is y? Well, we said y is x to the cosine of x. So times your y, so times x to the cosine of x. That's what the derivative of x to the cosine of x is. It's cosine of x divided by x minus ln of x sine of x times cosine x to the cosine of x. Woo! Okay, that's ready for a victory lap. Well, let's just last one. One more differentiation problem. And that is, suppose I tell you that f prime of x is 3x and f of 1 is 1. And I want to know what is f of x. Well, we know that f of x is going to be the antiderivative of f prime of x. So you're like, it's the antiderivative of 3x, which is just, well, you bump it up to x squared, and then you have to put the half out front. So it's 3 halves x squared plus some constants. It's like, okay, good. But plus what constant? Well, that's where this is going to help you figure it out. It's like, your f of 1 is 1. So I know that when I plug 1 into this guy, when I plug 1 into this for my x, plus some constant, he better come out to be 1. Because when I plug 1 in, I want to get 1 out. And so what's my constant? Well, that means this is 1.5 plus some constant is 1. So my constant must be negative 1/2. And so my function is actually, it's not just 3 halves x squared plus a constant. We figured out what the constant is. The constant is negative. This is messy. My function is 3 halves x squared minus 1/2. So you should think about what's going on here is your solution to f of x is actually a whole family of equations. You know, in your graph here, there's like, you know, when the constant is 0, when c is 0, it's just like 3 halves x squared. When it's 1, it's like a little bit higher. When it's negative 1, it's a little bit less. You have infinitely many possibilities for what f of x are, depending on what your constant is. And so what this thing here does, your f of 1 equals 1, is it says, oh, let's limit attention to the one that passes through that point. And once you specify this point right here, there's going to be a unique one of these solutions that passes through that point. And we're just figuring out the equation of that, what it is. Okay, so that is that. I'm going to stop there. And the rest of the review guide is integration problems. But we've done quite a few of those in class recently. So I think, yeah, let me stop here for now.